Hi everyone, today we will be covering the topic of van der Waals equation that we have previously covered in Module 3. So starting off with the ideal gas law. The assumptions for an ideal gas law state that atoms are point mass particles, meaning that they have a mass but no volume. There is great distance between molecules. Molecules only collide fleetingly. There are no forces between molecules unless they are colliding, and that molecules may gain or lose energy whilst colliding, but the total energy will remain constant. Although these laws apply to some gases, there are many limitations. Real or non-ideal gases diverge from the ideal gas law, especially when put under conditions of low temperature and high pressure. Now this is where van der Waals comes in. He formulated his equation in 1873. His equation explained why real gases derive from the ideal gas law under high pressures. His equation was essentially a modification of the ideal gas law that accounted for the size of the molecules and their interaction forces. Van der Waals' proposed equation is as follows. P plus n squared A over V squared times V minus NB equals nRT, where P is pressure, N is the number of moles, A and B are gas constants, V is volume, R is the universal gas constant, and T is absolute temperature. Now, how are the two gas constants A and B in his equation so significant? The two constants have been obtained from experimental data on density, temperature, and pressure. As these two constants approach zero, the van der Waals equation becomes the ideal gas law. The A and B constants differ depending on which gas you are using in your equation. For example, helium has an A value of 3.46 times 10 to the negative 3 and a B value of 23.71 times 10 to the negative 6. Meanwhile, neon has an A value of 2.12 times 10 to the negative 2 and a B value of 17.10 times 10 to the negative 6, and so on. The values are both considered to be correction terms in the equation. The A constant is a correction for the intermolecular forces, and the B provides a volume correction and is related to the non-zero volume of real molecules. In addition, the B constant is also an approximation of the molar volume. Now, what does it mean when these two constants have values greater than one another? So if the molecule has a higher A value, it means that there's a greater attraction between the molecules and therefore the gas will compress easier. Although if the molecule has a higher B value, that indicates that the gas particles are occupying a larger amount of volume. For example, chlorine is easier liquefied than ethane because chlorine has a larger A value and a smaller B value compared to ethane. Okay, now let's try an example problem and apply everything we just learned about the equation. The sample problem is as follows. 1 mole of ammonia fills a 7-liter bottle at 350 kelvins. What does the van der Waals equation predict that the pressure will be? Just a few things to keep in mind here before we get started on the problem is that the units given for pressure in this problem are liters, ATM, and Kelvin. Therefore, we will be using the R value 0.082057. Also, looking at the A value and the B value from ammonium, we get A equals 4.17 and B equals 0.0371. Okay, now let's try the problem. So starting off with the initial problem, we are first going to write out the initial equation that van der Waals had derived. So P plus n squared A over V squared times V minus NB equals nRT. From there, we are going to write out our known variables. So for N, we have 1 mole. For V, we have 7 liters. For T, our temperature variable, we have 350 kelvins. And then looking up the A and B for ammonia, for A we get a value of 4.17. And for B, we get a value of 0.0371. And then also looking up the relative R value to use, we are going to be using 0.082057. And our p-value we don't know, it's what we're solving for. And since we are solving for p, our next step would be to rearrange the equation to solve for p. So we would get p equals nRT over v minus nb minus n squared a over v squared. And then we are just going to plug in our values. And then just moving down one line for space purposes. And you're also going to notice a little typo come up soon. This part of the equation should be put over 7 squared instead of 7. So just keeping that in mind. We are then going to plug this equation into our calculators, and we are going to get 4.0679 minus 0.0851 and then just subtracting those, we're going to end up with a final value of 3.98. So we rounded to 3 sig figs. And then from there we can conclude that the pressure in this problem is equal to 3.98 atm. And that is all for today. Thank you for listening.